Okay, so for our group homework assignment, our group has chosen to do number 4, the work scheduling problem on homework assignment 1, the Gotham City National Bank. So obviously the first step here is going to be to identify the decision variables. So for this problem, we're going to have two different types. Okay, so the first type is going to be full-time bank tellers. So that's sort of defined for us here in the problem. So we can go ahead and use x1. So we'll let that equal the number of tellers that are starting their lunch at noon. And then x2, we're going to let that serve as the number of tellers taking their lunch at 1 p.m. Okay, so the second type of decision variables we're going to have to account for are the part-time bank tellers. So we know that that's in 3-hour shifts. Okay, so we'll let P denote the part-time tellers, and we're going to separate that into their shift time. So it's going to be P1, and we'll let that equal to the number of tellers that are working from start time 9 a.m. to noon. P2 will be the number of tellers working from 10 a.m. to 1 p.m. P3 will be 11 a.m. to 2 p.m. P4 will be noon to 3 p.m. P5 1 p.m. to 4. And lastly, P6 will be 2 p.m. to close, which is 5 p.m. Okay, so here we have our two sets of decision variables, P1 through P6, and then X1 and X2. So our next step here is going to be to define the objective function in Z. So we know kind of right off the bat here that it's a minimization problem. Okay, so we can also take what else is known here, and that's that full-time tellers are working 8-hour shifts for $8 an hour. Okay, and then part-time is working 3-hour shifts at $5 an hour. Okay. So we can kind of put all that together with Z. So Z will be 8 hours times $8 an hour. Times our first decision variable x1 plus 8 hours times $8 an hour times our second decision variable. So that's going to be our two full-time bank tellers. Okay, and then lastly, we're going to do 3-hour times $5 an hour to account for P1 to P6, which is going to be our part-time tellers. Okay, so kind of cleaning that up is going to be Z is equal to 64 x1 plus 64 x2 plus 15 times P1, P2 plus P3 plus P4 plus P5 plus P6. Okay, so here we have our objective function Z.
We're going to go ahead and establish the constraints. We're going to do this by breaking each equation up by the time period. So we'll start from 9 to 10. So from 9 to 10, we have both the tellers that are taking, the full-time tellers that are taking lunch at 12 and as well as 1. They both work 9 to 5, so they'll both be included. And then we also have some part-time tellers that are going to be starting at 9. So we're going to add P1. And if we go back to the problem, 4 are required. So at the very minimum. So we're going to do greater than or equal to 4. Next will be from 10 to 11. Once again, the full-time employees will be included. We're still going to have our part-timer number 1 since it's going to be from 9 to 12, so it'll include 10 and 11. And now we're going to also include P2. And for this one, it requires at least 3. (11 and 12), we still have X1, X2, P1, P2, P3. And we are going to need 4. Now, from 12 to 1 is when our first full-time employees go ahead and take their lunch break. So we are going to exclude X1 from this equation, and we're just going to have X2. P1 as well, their shifts already ended. They've only had 3 hours. So we're going to exclude P1, include P2, P3, and then add P4. And for this one, it requires 6. 1 to 2. Now the teller from X1 that had taken their break from 12 to 1 comes back, so we'll include X1, and X2 goes out and takes their break. So we'll leave out X2. P2 has completed their 3-hour shift, so we're going to go to P3, P4, and now include P5. And they need at least 5 tellers at that time. From 2 to 3, all the full-time employees have already taken their lunch break, so everyone's back. P3 has completed their 3-hour shift, so we drop them and continue with P4, P5, and P6. From 3 to 4, we have X1, X2, X4 drops off, so we have P4 drops off, I'm sorry, and we have P5, P6. That's it. And then from 4 to 5, 5 is the last, this will be the last hour of the workday. We'll still have X1, we'll have X2, P5 has already completed their shifts, so it'll just be P6, and they need at least 8. So those will be the equations for each hour. But then on top of all that, at most, 5 part-time tellers can be hired. So the way we'll show that is P1 plus P2 plus P3 plus P4. At most. All right. So now we have all our constraint equations. And then the next step will be to define the sign restrictions for each variable. So x1 and x2 all have to be greater than or equal to 0. And the same goes for p1, p2, so on. All must be greater than or equal to 0. They are non-negative variables. All right. To summarize everything, if we go back to our objective, it was to minimize the cost per day. And our equation for that was z equals 64 times x1 plus x2 plus 15, and then the summation from 1 to 6 for p of I. And this is the total cost per day for your full-time employees, and then cost per day for your part-time employees. All right, and then such that, and then within here, we're going to add all of those constraint equations from up top. Okay, and then is that all of them? We have all the equations, and now we're just going to add our sign restrictions for all of the variables. And there we go. Just going to add a note that these are non-negative. And this is our final solution.
Here we are in conclusion to this program with the outcome to minimize the cost to the Gotham National Bank returned the following values in the CPLEX program. The results, however, reminded me when Professor Vela quoted British statistician George Box. All models are wrong, but some are useful. In the case of this program, the values for both the part-time employees and the full-time employees placed us in a position to round the decimal numbers in order to provide a more realistic outcome. As we can see here, the CPLEX program generated an optimized daily bank cost of $467. In this case, well, actually $437.67. However, this cost was based on the following values. The full-time employees which need to go to lunch between noon and 1 p.m., represented by X1, which generated 2.333. We should actually consider rounding down to 2 full-time employees in order to report a more realistic number. In addition, for those full-time employees represented by X2, which went to lunch between 1 p.m. and 2 p.m., the generated value was 3.3333. In this case, we should actually consider 3 full-time employees to be more of a realistic number. In the case of the part-time employees, CPLEX provided the best average between 11 a.m. and 2 p.m., represented here by P3. The second best average came between 2 p.m. and 5 p.m., which was represented by P6. Okay. Now, this realistically can be rounded to 3. In the case of P6, the use of the part-time employees came to 2.33. This number can be realistically rounded down to 2. Now, clearly, these results are limited to the constraints which were placed by the Gotham National Bank in order to determine the optimal cost. That's basically what we have here. And that concludes my general presentation for what we were able to generate.